Good afternoon, everyone, and thank you very much for joining us. You're very welcome today on both sides of the Atlantic. It's a strange time that we're in, but we're going to bring you a slice of normality today by having our webinars as we usually do. Today's webinar is brought to you today by Dr. Stephen Walter, and his title for the presentation is The Implications for Estimating Treatment Effects when Trials Stop Early, either for apparent benefit or futility. So just a little bio on you, Stephen. So Stephen Walter received his PhD from the University of Edinburgh after faculty appointment at the University of Ottawa and Yale University. He joined the Department of Clinical Epidemiology and Biostatistics, which is now the Health Research Methods, Evidence and Impact at McMaster University in 1982, and he is now currently a Professor Emeritus. Dr. Walter has collaborated in research on internal medicine, evidence-based medicine, development, pediatrics, environmental health, cancer etiology, and medical screening. He is interested in several areas of biostatistical methodology, including the design and analysis of medical research studies, evaluation of diagnostic and screening data, risk assessment, and regional and temporal variation in health. He has published widely on these topics with over 500 refereed papers in biomedical and statistical literature. A recent survey of scientific impact places Walter in the top 0.03% of 7 million researchers worldwide. Wow, it's huge. Dr. Walter is an associated editor and then editor of the American Journal of Epidemiology for over 20 years and a section editor of the Wiley Encyclopedia of Biostatistics. He served as chair biostatistics in the International Clinical Epidemiology Network and has been involved in research capacity in the development in Asia, Latin America and Africa. Dr. Walter is a regular visiting professor in Australia and Finland and has been involved in research activities in several other countries. He is a past coordinator of the Health Research Methods program at McMaster and has worked with over 120 masters and PhD students. Dr. Walter has a huge array of honours and awards spanning his career, including being co-author on the Best Paper of the Year selected by The Lancet in the World Literature Series. So that's an absolutely incredible CV, and it just reminds us what an absolute pleasure it is to have you give your presentation with us here today. So before I hand you over to Dr. Walter, I'd like to turn everyone's attention to the little toolbar at the bottom of the screen. So if you hover over the bottom of your screen, you should see a Q&A box. So if you click on that throughout the presentation, if you have any questions, if you click on that and pop the questions in there, I can put them to Stephen at the end of the presentation. So without further ado, I hand it over to you, Stephen.
Okay, well, thank you very much. I have just come out of isolation yesterday because I was in Europe, in Finland, actually, trying to visit the university there. And I expect many of you will be also isolated at home. So as you said, this is very strange situation, but I hope this presentation will bring some measure of normality back to our lives. My title, as you, I hope, can see on the screen there, is slightly changed. I can't remember which one was the provisional one and which one was the final one, but anyway, it's much the same thing. I'm going to be talking about a variety of issues, statistically primarily, but also logistically, when one is considering stopping a clinical trial early for various reasons. And I hope that if people can't see my screen, that somebody will alert me to that. Okay, so here's my outline, and after that very long introduction, we're almost out of time, but I'm going to try and deal with all of these topics to some extent. I may have to cut corners a little bit towards the end, but here's our running agenda, and I'll come back to that from time to time. So we'll start off, first of all, with just a brief indication of some of the reasons why trials might stop early. We might, for example, have a look at the early data and see that it's suggesting significant benefit from the experimental treatment, which is so convincing that we feel, therefore, it's not really worthwhile to continue the trial to the end to confirm that message. The second one is the opposite, that the early data might suggest that the experimental treatment is actually much worse than the control or the standard treatment, and so that would be another reason to stop at that point. We also have futility. The early data, once again, may indicate that not much is going on, that the treatment effect appears to be small or non-existent. And so therefore we feel the picture is unlikely to change if we carry on, and so we'll abandon it. And also you have what you might call logistical futility, where it's been difficult to find enough patients, for example. Funding issues, of course, the funding scenario might change over time. The data might not be as good as we'd hoped for in the design, and some other reasons here. Generally speaking, when we're doing trials, we have the notion that we'd like to reach a decision as quickly as possible, and also by doing so, put as few patients as possible on the inferior treatment. Also, apart from our own trial, we may have other things going on out there, and there may be new external evidence that comes in, for example, another trial on a similar topic that changes your opinion about the value of the treatment that you're considering. We have issues of energy and human resources, just fewer patients in total, and we want to try and get a fast result. We may have a change in priorities, so we may be missing some opportunities by using our patients in the current trial. We may decide to change our minds about that. And lastly, here we've got the possibility of legal action, and I'll mention, I hope I have time for this, we'll mention one example where this came up. In my group, we've done a series of studies that are referred to generally as Stop It. There have been a series of these investigations, and I will summarize this literature at the end. I'll put a slide up at the very end that has some of the key references if you want to look further at this. But this particular part of Stop It looked at a series of trials, and out of just over 500 trials, found that 78 or 14% had indeed stopped early. About half of the time that was for benefit, about a quarter of the time it was for harm, 9% of the time it was futility, and then 12% for other reasons, including poor accrual. And these were in top journals during a 5-year time period. Now, I mentioned the idea of having an early look at the data, and this brings up the question of interim analysis and what should we do. Some of this may be familiar to the statisticians, but I understand this is probably a mixed audience, so I will go fairly basically in these various topics. The idea of interim analysis, that is looking at the data from time to time as you proceed, brings up the problem of how do we assess statistical significance. And it's very similar to the multiple testing problem. If we carry out more significance tests, then the probability that something will show up as apparently significant will increase. So the rate of incorrectly rejecting the null hypothesis, that would be of no treatment effect typically, is going to be larger than the nominal type 1 error. And this is a particular problem at the beginning because we have these trends in the data that may appear and then disappear. So here's the general idea that we're thinking about. We have the treatment effect on the y-axis there and the evidence accumulating over time. The blue line there is where there's no treatment effect. If we're above the line, the experiment is showing benefit. If it's below the line, it's showing harm. And the yellow line here is what we'd like to finally conclude as the true treatment effect. But as the trial goes on, you'll see that this is obviously schematic. We have a lot of fluctuation at the beginning because of very few observations. And gradually, assuming that there's no other bias present, we hope to converge to the true effect at the end of the study. So the general problem of looking early, of course, is that we have what are sometimes referred to as these random highs in the early data, or possibly random lows, which would exaggerate the apparent effect in one direction or the other. And this is a well-known table to many people. This actually tells you what the type 1 error is going to be if you carry out a number of independent tests, and you can see it goes up progressively from the nominal 5% if you just do one test. So this is the basic issue here. Now, to compensate for that problem, these so-called group sequential methods have been developed, And they allow you to do repeated testing at interim analyses while still preserving the overall type 1 error rate. So we define a boundary, which is sometimes called a stopping rule, sometimes a warning rule, sometimes a guideline for this monitoring on a group basis of what's happening in the early data. And it tells you the criteria that you would have to reject the null hypothesis at a given interim analysis. These methods are typically known by the names of their authors, and I'll be considering three of the most common ones: Pocock, O'Brien-Fleming, and Hay-Bittel-Peto. There are also a more flexible set of methods, these sequential methods primarily developed by Lan and Demetz with so-called alpha spending. And they're flexible because you don't have to decide in advance what your analysis plan is going to be. And you can so-called spend your alpha, that's the type 1 error rate, as you go along accordingly. I'm not going to say any more about this particular area, but I encourage you, if you're interested, to look at the University of Wisconsin website, where there's some useful software where you can develop your own flexible guidelines of that type. Okay, so here's the general idea. Once again, we have this true treatment effect, and because of the early data with all this fluctuation going on, we may experience a situation where at some point where we might do an interim analysis, we've exceeded the boundary or the threshold which defines a stopping criterion. The boundaries look like this. On the left-hand side, we've got those three particular guidelines according to Pocock, O'Brien, and Hay-Bittel. And with one-sided testing, the y-axis here is a normal variable, a Z statistic. So in the usual circumstances, at the 5% level for alpha, you would be requiring the Z value to be more than 1.64. That leaves 5% in one tail of the standard normal distribution. But these group testing algorithms instead require a much greater effect early on, and how much greater depends on the particular rule that you're using. So you can see that Hay-Bittel and O'Brien actually require you to be at 3 standard deviations or more. But then in compensation, you have a slightly less stringent test at the final analysis. This particular diagram is for 2 interim analyses followed by 1 final analysis. In contrast, Pocock requires a value which is rather close to 2 for each of those 3 tests. And on the right-hand side, you have a similar pattern for 2-sided testing. Well, now let's have a look at some of the empirical evidence for what's going on in trials that stop early for benefit. And this again is part of the Stop It results. This particular paper by Dirk Bassler and myself and other colleagues about 10 years ago now in JAMA. And this was a systematic review of studies that had actually stopped for benefit. Typically in favor, well, obviously in favor of the experimental intervention. And if you're interested in the details of the search algorithm, you can find them in the JAMA paper, but these were major journals, and we did duplicate extraction of data and assessment of eligibility of the papers. So we came up with 98 trials in this particular series, and 54 of them didn't report one or more of fairly major things: the planned sample size, any details of the interim analysis when the trial did actually stop, and importantly, whether the stopping rule was actually the reason that informed the decision to stop the whole trial. Most of these trials, or yes, about 3/4, I guess, most of them used dichotomous outcomes. And so we were able to do more detailed analysis on that set, and we found that the trials that had fewer events were the ones that typically had larger treatment effects. And that's what you might expect because of this random high phenomenon in the early fluctuations of the data. We also, as part of this work, we looked at studies that had stopped and then a series of matched trials, over 400 of them, that were looking at the same clinical questions. So we had 91 trials that had stopped, asking a variety of questions, not 91 because some are on the same issue, and then 424 other trials that had not stopped on the same clinical question, and compared what we saw as the results. And it turned out that the pooled ratio of relative risks in the stopped studies, or the truncated studies as you see it there, versus the non-truncated trials was about 0.71. So that means there was about a 30% additional treatment effect in the stopped studies. And that difference was independent of which stopping rule had been applied, and also independent of things like blinding, concealment, and other aspects of the methodological quality. Now, also very interesting from the clinical perspective, when we looked at the non-truncated trials and did meta-analyses on those, the pooled effect in those trials on the same questions failed to demonstrate any significant event. So it does appear that at least the stop studies are giving you a larger estimate, and it's probably an overestimate, and indeed it may not be an important treatment effect at all. Okay, now switching gears a little bit, I'm going to talk about how we can consider the effect of this early stopping on the estimated effect size. And again, this work would be cited for you in the references at the end, but this particular summary I'm going to give you is based on a Statistics in Medicine paper from 2017, which involves a little more theory. So as we've seen, the literature in this area mostly has focused on the inferential properties of multiple testing, in particular to try and control the type 1 error rate. But out there's not so much advice about the estimation of the treatment effect. And I think you will have seen from my diagrams that if you have a study that does stop early on one of those random highs, you would tend to overestimate the benefit. And if you, in contrast, decide not to stop with one of those stopping rules, the compensating effect there is that you'll tend to underestimate it, which is a little more subtle to think about. That's true. Just by virtue of having the stopping rule in place, even if you don't stop early, there is an impact on the estimated treatment effect. And finally there, what's the situation for the study as a whole, whether it stops or not, or the group of studies in that category with the stopping rule, will we have any bias associated overall? So what we did was we actually looked at the theory here, and we developed some analytic expressions for these various quantities of interest. How much do you overestimate the treatment effect in studies that stop early? How much do you underestimate in studies that don't stop? How likely is it to stop? What's the overall bias in studies that have a stopping rule and they may or may not stop? And I won't say much about number 5 there, but there's also a question of how much weight the stopped studies would have if they're included in a meta-analysis. So we developed these expressions and then evaluated them for realistic parameter settings. So just a little bit of algebra here. We assumed a normally distributed outcome variable, and the idea would be that we stop at an interim analysis if our test statistic Z exceeds a certain value with a certain alpha level that would be defined by the stopping rule. And here it just shows you for one-sided testing, but obviously there's an analogy for two-sided testing. And that defines in turn a critical effect size, which is related to those things, plus involves the standard deviation of your outcome. But without any loss of generality, we can just take the sigma, the standard deviation, to be 1. The key analytic result is to find the expected value of a normal distributed variable with mean mu and standard deviation 1, which is potentially truncated at these points A and B. And you can do one or you can do both at the same time. So you could be stopping the trial by truncating if you have a high estimate of treatment effect, or a low estimate, or even both. Stopping rules can involve both sides. So that was the key analytic result that we were able to use, and we evaluated this for various parameter settings. So the true mean we took to range from 0, that is no treatment effect at all, up to 1 standard deviation, which is a very big effect. And we ranged the sample size so that we would have small, medium, and large studies with 80% power for these various particular effects, which some people have called small, medium, and large size effects. We worked all this out for situations with 1 or 2 interim analyses using those 3 stopping rules that I mentioned. And again, just a last bit of algebra here. Here are the analytic results that we got, which aren't all that difficult to derive actually, but the important thing here is, first of all, the mean in studies that did stop is the true mean plus something. So this is telling us that we do in fact have overestimation in a stopped study. At an interim analysis, but if you don't stop, there's a compensating negative contribution there. So this is underestimation. And in non-stop studies at their final analysis, it's still negative. The probability of stopping is quite easy to work out. And then finally, the mean here is also the true value plus something. So we have a positive bias in any study that has a stopping rule for benefit. And as I said, I'm not going to be talking about the meta-analysis issue. So to summarize some of these results, we found, first looking at that first quantity, how much are we overestimating if we do stop early? It turns out that's more of a problem if the true mean is small or if the total sample size is small. And those are perhaps intuitively somewhat clear. But even in other situations, even with quite large N, you can still have a bit of a problem here. So this example is with Pocock rule, and a trial of 800 people. And so if the true mean is 0.2, which is a moderate sized effect, you'll overestimate it by 0.07, which is about 1/3 of the true effect. And it gets worse if you have a really small effect of 0.1 standard deviations. You're overestimating by 0.14, which is actually more than the true effect size, 143% as it says there. And here's some graphics, which again, you can look at the paper in detail, but you can see the overestimation on the left-hand side here. These 3 is for one-sided testing with the 3 rules, and on the right-hand side, it's for two-sided testing. So for one-sided testing, the small studies, the red lines, have more of an issue. They're more overestimating, but the problem goes away somewhat if you have a larger true value mu in the x-axis. On the right-hand side with two-sided testing, it's somewhat similar, but there's an intermediate point where the overestimation is most serious, and then after that it tails away again. Now, moving to the second quantity, the underestimation in studies that do not stop. So you did an interim analysis, but the threshold was not crossed. Again, there may be a significant problem here. So here's the same example, Pocock with 800 patients. And so with these 2 values assumed here for the true effect, 0.1 and 0.2, this is the degree of underestimation, which is, a non-trivial percentage of the truth. And this problem gets worse if the true effect is large, or if the sample size is large. But fortunately, in either of those cases, you're less likely to cross the stopping boundary. So you're less likely to be in this situation. And here again is a graphic for how that looks. Again, the small studies are on top here, which means actually less of a problem if you don't stop. And the problem gets worse in this case for a larger value of mu, the true effect. Here's quickly a plot of the probability of stopping early. So small studies are less likely to stop, which is good news and again, intuitively reasonable. And obviously you have a larger probability of stopping if you have a large treatment effect because it's a little more obvious. Now for the overall bias, this one is a little more complicated, but once again, we do have an intermediate maximum for the bias, and small studies again do worse. Somewhat similar patterns with one- and two-sided testing under the 3 rules. Just to summarize that for the overall bias, it goes down eventually, goes down with n, with the sample size, but with a fixed sample size as a maximum at that intermediate value. And just to give you some numbers here, the maximum that we found in absolute bias, if you had a trial of 100, is about 6%, but goes up with a smaller value of the sample size. The maximum relative bias is about 10% of the true effect at that stage. Not a huge difference between the stopping rules, but interestingly, even if the true mean is 0, all of the stopping rules have a small positive bias, that is with one-sided testing. That goes away with two-sided testing. Now, here's a very interesting result that we were able to show analytically. This is a table, again, from that paper, showing you the maximum possible bias and the treatment effect at that bias, and then the relative bias. So very interestingly, the maximum absolute bias is independent of the stopping rule that we use, and the relative bias is independent of the study size. And this, of course, gives you some guidelines as to how big those things might be. You might say, well, can we improve things by cranking up the study power? And of course, you do that by increasing the sample size typically. So the problem of bias, this is the overall bias, does reduce slightly. We push these curves down a little bit as we increase the power from 80 to 95%. And the mean goes backwards a little bit towards small values of mu, but fundamentally not a huge effect, somewhat surprisingly. So a summary on all of that, stopping for benefit. Stopping early often will substantially overestimate the true treatment effect, and studies with a stopping rule that don't stop early can still underestimate the treatment effect. And this is, I think, a point that's been less recognized. The overall bias in studies that have such a stopping rule is small, usually about less than 10% of the true effect size with one-sided testing, or, and I didn't show this in detail, but it comes out slightly larger with two-sided testing at 15% if you have a sample size of at least 100, but it gets worse with smaller sample size. We've done all this with up to 2 interim analyses, and we expect that the trends that we described would continue if you have even more than 2 interim analyses. And a thought here that, of course, we used a normally distributed outcome, and I said earlier that the majority of papers actually use a binary outcome. I don't think that's a real issue because we do have the central limit theorem to appeal to, so that approximately the distributions of the test statistics would be the same for other types of data. A question that often comes up is, well, now we've got this bias and misestimation going on, can we correct for it? Unfortunately, I think the answer is no, because the corrections will depend on the unknown parameter. And what is that unknown parameter? It's the true effect size. And if we knew that, we wouldn't be doing the trial in the first place. That's the whole point of doing the trial. And also, if we do attempt a correction, even if we knew that value, it does rely on some assumptions about past and particularly future data, which can't be verified. Bayesians have thought about this issue as well, and they have developed a few methods to help here. But in our surveys with the STOP studies, we found that these have not been used. We actually found no convincing examples where Bayesian methods have actually been used in real trials. So that's all I'm going to say. I think we're approximately on time here. I'm going to move now more briefly to a brief discussion of stopping for harm, and then we'll deal with futility. So stopping for harm, this is where you think that the experimental treatment may actually be worse, or possibly it could be a safety issue, of course. It may have more side effects. And we tend to err on the side of caution here, and so you may have asymmetric boundaries for stopping. Here's a particular example, probiotic treatment for severe acute pancreatitis versus placebo. And this is the table as it existed at the single interim analysis that was done. In the treatment group, the probiotics, we have 15% death rate with 14 deaths, and in the placebo, less than half of that, 7%, with only 6 deaths. And I did some Fisher's exact calculations here because the papers did not provide that, but this is my calculation. And it's a kind of borderline effect in terms of statistical significance. It's a large relative risk, of course, it's more than 2, but arguably not significant yet. So the Data Monitoring Committee obviously had a look at this, and this is what was reported in the final paper, which tells us about the existence of that interim analysis. And it said, although 184 patients had completed, a blinded interim analysis was done. Sorry, after 184 patients had come in. There was a non-significant difference in mortality, 0.1 for the p-value. And rather strangely, the monitoring committee concluded this had been somehow caused by skewed randomization, as they called it. And they give some arguments as to why they thought that was the case. And they also argued that the overall mortality was well within what you would expect overall for the 2 arms combined at about 11%. So according to this predefined stopping rule, and they had one, the monitoring committee decided that the study should be completed. And indeed it was completed. And this is what happened. So now the same table now showing the results at the end in the completed trial. And we see that the death rates in the 2 groups are almost the same. And in fact, the difference has even slightly widened. It's now 16% versus 6%. And if you redo the significance testing, it's highly significant, both 2-sided and for either side. So this particular trial then had a stopping rule. An interim analysis was done, but nevertheless, the completed planned sample size was achieved and was obviously criticized post hoc. Statisticians and some methodologists publicly criticized it, saying that the monitoring committee had actually been negligent in missing that early trend of increased mortality. And this was the legal argument that I mentioned. Relatives of presumably later enrolled trial participants launched a website saying you should have known that this was a bad treatment. So this is arguably an example where they had a stopping rule, they used it, but unfortunately it seems to have led them to the wrong decision. Okay, so now on to the last major topic, which is stopping futility. And I'm going to talk about the general impact of futility stopping on the estimated treatment effect again. Once again, a little more theory and some empirical evidence on trials that actually did stop for that reason. So here a slightly different diagram with a path in the data early on that actually shows a dip and then coming back to a no effect situation. So you have to ask now, well, what would happen if you did an interim analysis at points 1 or 2 where not much seems to be going on? You might think at that point that it's unlikely you're going to get an important result and therefore decide to stop. So this might be a random low or a random 0, you might call it. So we can consider stopping early if the interim results show a limited treatment effect. And one thing that has been recommended in this case is to calculate the conditional power at that point. And I'll explain what that is in a moment. But the idea is that if that power is low enough, we think that the study is unlikely to show an important effect at the full sample, and so decide to stop. Empirically, people have used a threshold there of about 10 to 20%. That is, your power must be greater than that to allow you to continue. So conditional power, more exactly, is the estimated probability that if you were to go to the final sample size and all the patients were followed up for outcome, and conditional on what we already have at the interim analysis, that the result would be statistically significant at the end. Now, to make that calculation, obviously we have to assume something about what's going to come in for the future data. And the 2 main options that have been used here are, one, to hang on to what you thought at the beginning in the protocol and therefore retain the original design treatment effect. We say that, well, we went through all that effort to create the protocol and design the study, we'll continue to believe that protocol or design treatment effect size. Number two there is that we now do a little updating mentally, and we assume that the current trend in our data as seen at the interim analysis would continue. So once again, with that background, we did the same things before for benefit. We estimated all these quantities or developed expressions for them. The underestimation now for studies that stop early. This is, of course, a kind of mirror image of what we had before for benefit. Overestimation for studies that do not stop, the probability of stopping early, and again, the bias for studies with such a stopping rule for futility. So we looked at those again for realistic scenarios, and then we looked at empirical examples. This is quite similar to before. We assumed equally spaced analyses, but we did have to assume either the design or the current trend hypotheses. These are new things, of course. One or two analyses, normally distributed outcome, and so on. A range of these parameter values, more or less as we had them before, and we calculated those quantities of interest. I'm going to go fairly quickly over the results. I'll just summarize them, but here's a graphic showing you the estimation error, that is the misestimation for studies that do stop for futility. So you can see that one of the things that shows up immediately is that the blue lines are quite different from the red lines. The blue lines are what happens for conditional power and estimation error if you maintain the design effect. And the red lines are what happens if you update and use the current trend. So and of course we don't know which of those is actually the right answer, but conceptually you would have less estimation error if the current trend was indeed accurate. Also, these lines are all going downwards to the right, so more of a problem if the true effect is large. So you stopped, but with a large effect, you make more of a mistake. So just to summarize all of this, as we just saw, underestimation in stop studies is a greater problem with the design assumption than the current trend hypothesis. It's a bigger problem when you have a big true effect. And it's, I didn't show this numerically, but it's quite large relative to the true mean, regardless of the assumption that's made. The overestimation in studies that have a rule but don't stop, the pattern is more similar between the assumptions. It goes down with the true mean for either assumption. And once again, as we saw for benefit, the impact of improving study power is quite limited, but you do get somewhat less overestimation and lower probability of stopping if the power is increased. For the overall bias, it is a negative bias. And again, this is a mirror image of the futility, of the benefit situation. Typically small, so less than about 0.12 on the normal 0.1 scale, but goes up with the design treatment effect size. It's a rather complicated pattern, which I won't go into in detail, but it depends on mu, the true effect, and which assumption you make about future data. In particular, with the design assumption, it decreases. This is the overall bias decreases as mu increases, but with the current trend, it has much more complicated pattern with a negative upper bound, which we were able to find analytically. And comparing the situation for 2 interim analyses compared to just 1, the bias is worse. And that's a general trend in all of these results. If you do more interim analyses, all of these issues become accentuated. Okay, so now let's have a look at some empirical data or empirical findings from literature. So we've seen that we can have substantial misestimation with a futility stopping rule. And we wish to now survey the literature and find out what's going on out there in terms of current practices in deciding to stop a trial for futility and see how it's reported. So this is also, once again, part of the Stop It series. In this case, we Through filtering a very large number of trials with a systematic search in the literature, we identified 52 trials that had actually stopped for futility, and we extracted a huge amount of information, both statistically and clinically, and I'll just have time to hit some of the highlights on this. Once again, just a little bit of theory here. How do we actually get the conditional power once we've seen the interim analysis? Well, the conditional power here, the expression, is a function of what the true effect size is, first of all, and it's also a function of when you do the interim analysis, which is usually measured by what's called the information time, or sometimes the information fraction. So it's essentially how many observations or events do you have out of the number that you would expect in a completed trial. So you can actually work out the conditional power if you have that information. Just to give you a sense, if you can read this, I hope, on a screen, but this is showing you just some of the papers that we extracted among the 52, showing you the authors and the subject. So a wide variety of clinical conditions being treated in various ways. We looked at whether the futility analysis was planned, what the basis for a stopping rule for futility might have been, and how many interim analyses there actually were for futility. So first of all, was it planned? Good. At least 3/4 of the time it did seem to have been planned, 38 out of the 52. Not planned in about 10% for all these various reasons, including this is, if you like, the logistical futility of slow patient recruitment. In this case, there was an interim analysis for benefit, but they also looked at futility at the same time, decided to stop for that reason, and so on. External evidence coming in from another study. And then we have 8 trials where we couldn't really tell if it was planned or unplanned. If these analyses had been done, and if they stated, the most usual number of analyses was actually 1. But of course, if the report doesn't tell us in full about what the analysis plan was, it's possible that there might have been later analyses done had they not stopped at that point. We don't know that. Now, what are the criteria that was stated up front for stopping the trial at an interim analysis? Well, now, not so good. In more than half, there was no stated criterion. Some used threshold values. A few used actually conditional power as their guideline. Some used p-values, and others used very vague, non-specific statements, something to do with futility, but not very detailed. Now, this table shows you some of the information that we extracted on the statistical features. So we have the planned total sample size here, type 1 error, 1 or 2-sided testing, the planned power, type of variable that we had, what it actually was clinically, what the null value or control value was, and the design hypothesis. So this is giving us the design treatment effect size. And we also have the results. So we have the information percentage at planned interim analyses and the actual information percentage then, whether authors reported futility just by claiming it or whether they gave us some more detailed analysis. The detailed basis for actually stopping, because of course it may not be futility itself. The main result, and whether we could actually get the conditional power out or whether the authors had themselves reported it. So when was it done? When was the interim analysis done? Now you can have multiple categories here. It was sometimes specified as a percentage of the number of planned patients or events, sometimes as a number or sometimes as a fraction, such as a half, for example, sometimes at a particular time point, a calendar time point, like annually, but about half the trials didn't tell us. So this is, of course, an important feature of the analytic plan. Why did they actually stop? Well, a little less than half said it was futility, typically when discussing what they call disappointing results through a lack of treatment effect. And then some people stated beliefs that the results probably wouldn't change, or that the trial had already failed to show anything, or that the final results would not be statistically significant. Some stated, only 3 though, that it was actually low conditional power that was the specific reason for stopping, or some had a pre-specified stopping boundary from the rule that had been crossed. But very often it was a verbal summary, somehow relating to futility in our judgment, but some of them were quite interesting. Some said things like conditional power was nearly 0, so I don't know if that means they actually calculated it or not. Some said there was almost no chance, or it was unlikely to achieve statistical significance. One actually said it was impossible to demonstrate efficacy, and I don't know how you would conclude that with statistical variation. How this futility was described. Often futility was mentioned or claimed, but there were no details at all. That was the largest group. We sometimes got something about an analysis of futility, but no statement about conditional power. There were 11 trials that did give us conditional power, but there were some issues with that group, as I'll mention in a moment, and a couple that were unclear. So estimation of conditional power was reported in those 11 trials. In 16, there was not enough information to get it, but in 25, which is about half the sample, we were, by a huge effort, because all these studies had different features, of course, we were actually able to calculate it. So this is our finding for the conditional power among the 25 where we did the calculations. And you can see that if you assume the current trend, most of the time the power is actually very low. Conditional power is lower than what you might think of as a nominal threshold of 15%, let's say. But if you retain the design hypothesis, quite a lot of these studies had substantial conditional power. In fact, the largest one we found was 73%. So clearly the decision and the interpretation of the rule depends very much on the hypothesis that you adopt at this point. However, in the 11 where authors reported conditional power, only 2 of them told us what their hypothesis was, and that was current trend in both cases. So again, this is a lack of detailed reporting that really prevents us from interpreting what they found in detail. The last thing we looked at was whether the interim analysis had actually made any difference to the recruitment of patients. And in just less than half, it did seem that accrual had stopped immediately. In another group, almost the same size, there were additional patients that showed up in the final report, and that's of course because you have follow-up still continuing. And I've got a little asterisk here to remind me that there was actually one trial that we found where the final sample size actually exceeded the original target. So in that case, you would say that the futility analysis that they did was itself futile because it made no difference to the execution of the study. So a summary here of all of that on futility. We feel it's the empirical evidence was that stopping for futility was reasonable in many cases if the current data trend is accurate. And we know that that may not be true because of variability, but it's certainly questionable in some cases if the design parameters from the protocol are retained. Reporting was often poor. This is often the case, of course, with this kind of investigation. And in particular, it's often unclear if the interim analysis had been planned in advance or if other analyses might have been done later. Many trials claimed futility as the reason for stopping, but without any details. Only a few gave us conditional power directly. And many studies, we think, had substantial conditional power if you retain the design hypothesis. And in the back of all of this, once again, we have the potential for misestimation of the treatment effect in both the stopped and non-stopped studies in trials that had a stopping rule. So in conclusion here, just I think got a couple more slides and then we'll be done. These studies are quite difficult to interpret if they fail to tell us if the interim analysis had been planned or executed. If they do stop early, they should really tell us why, including the assumptions made about future data, because that's for conditional power. If they don't tell us that, it's very difficult to assess the impact on estimated treatment effects. Now, an important point here, I think, is that we may not realize that stopping rule usage is probably much greater than it actually appears, because the reports may not tell us, particularly if a study goes to completion but had a stopping rule, interim analyses were done, but they are not reported. So the study goes ahead and completes, but we never know that there were interim analyses. So this is our obvious recommendation from all of that, that clearly we have greater interpretability of truncated trials if we could improve the reporting of the protocols and how they were actually executed. So recommendations, if you have a data safety monitoring board, of course not all trials do, but it's a good idea to establish rules and roles and the decision-making processes at the beginning. Set a reasonable target sample size to allow you to identify the treatment effect. Set the stopping rule, and you can call it a warning or a guideline if you like, and those boundaries ahead of time. And be aware of the impact of the stopping rule on the estimated treatment effect. And before you finally do decide to stop, you need to carefully consider other things, other reasons for the results that you're seeing early on. Are the prognostic covariables okay, distributed nicely? Any other form of bias? Any missing data? Differences in adherence to the treatment versus control, co-interventions, and so on and so forth. And you may also want to think about the impact on future research, because if you come up with an early result, say showing spectacularly good benefit in early data, that may have the impact of discouraging anyone else to do confirmatory studies. So it may impact not just your work, but other people's as well. And last of all, apart from references, I think, is my great hero, Gary Larson, the cartoonist, who I believe might even be coming out of retirement quite soon. This is his design of a study to find out if laughter really is the best medicine. And there's a lot that one can say about this particular experiment, such as simultaneous interventions and non-independent assessments of outcomes and so on. But I love Gary Larson's work, and there's always a cartoon that fits the bill. So last but one, this is showing you my colleagues who've done a lot of this work. Guyot and Schandelmeyer at my University of McMaster, Hedan Han, who was a student of mine, now working in Toronto, and two colleagues, Basler and Brielle, who are in Switzerland and have been doing all the heavy lifting on the Stop It studies. And I'll leave this one up now. This is really my last slide, and these are the key references. I think these slides will all stay on the Trials Network website. That might be confirmed, in which case you can have time to copy them down in more detail at that point. So thank you for listening. If you're still there, I can't actually tell.
Yeah.
I hope somebody's still out there. And I think we might still have time for questions.
Brilliant. Thank you so much. That was really, really good, Stephen. And really great practical advice there as well. You know, it's good to have all those references, and we definitely will have all these, this presentation up on the website as well. So there will be lots of opportunity to take them down. Had a couple of questions. Now, one of them came in just while you were on the topic, so I'm going to try and put it into context, but I may well get this wrong. And that question was, when you were talking about conditional power in the stopping for futility segment, and the question was, would these results be expected to be generalizable to multi-arm, multi-stage designs, or drop the loser, pick the winner designs? I don't know.
That's an interesting question, not one that I've considered in any detail. So this is just off the top of my head. I think one could certainly calculate conditional power for multi-arm studies. Perhaps the issue that would arise, therefore, would be, once again, multiple comparisons. And of course, multiple arm studies do try and allow for that in normal circumstances. But I'd need to think about that in more detail, but presumably you'd want to think about the estimation of conditional power, taking into account the fact that you've got several such calculations and they would obviously be correlated as well because they're coming from the same study with perhaps multiple comparisons to the same control group. Yeah, I can't say any more in detail about that because that's a new topic which I haven't really thought about.
That's fine. Okay, another question then we have from Finbar, and he says, many thanks for your presentation. What about trials planned with interim analyses for both efficacy, harm and futility? Could estimation biases cancel them out?
Well, sometimes yes, sometimes no. It depends. As I think I mentioned, you can have stopping rule boundaries that are on both sides. So you could have, let's just say for the sake of argument, you're using Pocock and, no, let's not do that because I can't remember what the number is. Let's say you have a rule with a threshold for a certain number of standard deviations to declare significant benefit and stop. And you also have a boundary on the other side for harm, which would be at the same distance, same number of standard deviations, but in the other direction. In that case, very often the bias will cancel out. The overall bias will cancel out. But you still have the problem that if you do stop, then you would have misestimation of the treatment effect. So if you happen to cross the benefit threshold, then you are still overestimating. Now, having the boundary two-sided like that obviously affects what the boundaries are, so the degree of misestimation would be different compared to only allowing stopping for benefit and not for harm. Concerning futility, I think that's usually put in a slightly different category. Benefit and harm often do go together, but futility is often considered separately, although as I mentioned, there was at least one example we found where people had done an interim analysis for benefit and then actually found futility was going on. So,
yeah.
so the two can be mixed up in practice.
Okay, moving on to another question then. How closely should investigators adhere to the results of interim analyses with respect to the stopping rules?
Okay, well, I think the question there is, as statisticians, we probably invented the terminology stopping rule, but it really isn't a rule. It's just one of the factors that comes into play as you interpret an interim analysis. So as I think I tried to mention very early on, that there are a lot of other reasons why you might want to stop at an interim analysis other than just what the stopping rule or guideline is telling you. So things like logistics, external evidence, and all of those other things. I think all of that has to be put into the mix, and then the DSMB or the monitoring committee has to consider all of those things in its wisdom. And of course, there are many documented examples where the Data Safety Monitoring Board overrules what the statistical threshold would tell you in both directions. There are examples in both directions. The probiotics one, for example, you could argue there was a pretty strong signal to stop, but they didn't. And in other cases where the stopping rule has not crossed the boundary, but the monitoring committee decides to stop because it's a close call or with the other factors being considered at the same time.
Mm-hmm. Okay, I think we have time for one last question, if that's okay. Given all the problems you've mentioned with interim analyses, perhaps it would be better not to do them at all. No.
Yeah. Well, I think the answer to that depends why you're doing an interim analysis. And I think it's perfectly legitimate to do interim analysis for safety, for example, looking at side effects, because you can do that independently of what your primary outcome is, essentially. But I think you do have to be very cautious about interim analyses for the main outcome, for all of the reasons we've discussed. But in addition, the investigators will usually know, almost always will know, that an interim analysis is being done. And so if that happens, and even if they're blinded to the result, the fact that the interim analysis was done and then they are told to continue actually does convey some information about what's happening in the main outcome for the trial. So it's a tricky situation. My colleagues, some of the people, the leaders in evidence-based medicine, are now tending to argue to not do interim analyses at all if you can possibly avoid them, at least interim analysis based on the primary outcome of the study. So yeah, and obviously it is important to get, as I keep harping, it is important to get a good estimate of the treatment benefit at the end of the day, so that we can get a valid estimate of what we're getting in terms of this new treatment versus control. And we can assess those benefits versus other considerations such as cost effectiveness, NNTs, numbers needed to treat, and so on. All of those kinds of things, which you can only really get through a completed study.
Yeah. Okay. Thank you so much, Stephen. That was absolutely brilliant. Really, really enjoyed it.
Thank you.
And your slides are fabulous as well. So just to say thank you again. Thank you to everyone that joined us from home, and I hope you found it as helpful as we have. And just a reminder again that those slides will be up on the HRB-TMRN website. So and it's great to hear that you're out of quarantine, Stephen. That's brilliant.
Yes, I can actually meet my wife now for the first time for quite some time.
Very good. All right. Thanks again. Bye-bye.
Okay.
Lovely to have
Yes.
you. Bye-bye.
Bye-bye.